Welcome to part 5 of the Classic Ladder basic tutorial for LinuxCNC. In this lesson, I want to go over timers and counters and how they play a vital role in your PLC programs. So in its simplest form, a timer is sort of a type of counter in that it takes an input signal and it counts either up or down depending on what the timer is set to do, and that count will either enable an output for a certain amount of seconds, or it will delay the triggering of the output for a certain amount of seconds. And to show you that, what I'm going to do is I'm going to create 3 counters. And you'll notice that over here we have the timer number, which is just the number of the timer that we're using, sort of like how we have our various inputs and outputs. We have I1, I2, I3, Q1, Q2, Q3. This is just the timer number respective to the timer that we're using. The base is the number of minutes, seconds, or 100 milliseconds that the timer takes to enable or disable. The preset time is just the number of units under base that we will allot for the timer to actually perform its task. And then the timer mode, T on, T off, and TP, which is kind of like timer permanent. So, to show you a couple of different methods of using the timers, let's go in, create a couple of outputs. Let's say Q10, Q11, Q12. And I'm going to define an input called input 10, and I will share that amongst the 3 timers. So now that we have that set, we can go to our HAL configuration. And we're going to use a set P classicladder.0.in-10. Set that to true. And when I enable that input, we'll see a couple of things happening over here on the Classic Ladder window. On timer 0, there's a 10-second delay before the output is actually triggered. On timer 1, the input is triggering the output already, but the timer does not turn off the output for 10 seconds after the input is released. And at the bottom, the TP, it gets the input, it counts down, it doesn't care how long that button is pressed. It gets the action, it does the permanent timer setting of 10 seconds, and it disables the output after that time is allotted. So you can see right away that there's a difference between the 3 timers, even in this rudimentary example. A quick way to make the off timer respond more for quick user input would be to change the input style from a standard normal open to a rising edge. And once you press the button, it becomes a momentary input that triggers the output. If you want to hold your finger on said button and have it delay the beginning of the counter until you release your finger, that's where this comes in handy. Now the permanent one, it doesn't care how long the input is triggered, it just wants to count. That's all it wants to do. It gets the signal and it counts. You can remove the input, you can e-stop the machine, you can do everything in your power to stop this timer. There's nothing that is going to stop this from counting. So that's the benefit of the permanent timer. So to show you that a little bit better, what I can do is I can go into the editor, modify, select these timers, and we will make them all 30. So now they all have a time of 30. I'm going to tie classicladder.0.in-10 to the HAL UI pin for machine is on. And we're going to say net machine -on HAL UI .machine .is -on and tie that to classicladder.0.in-10. So we'll see right now we have timer 0 counting up to 30 before it triggers the output. Timer 1 waiting for the release of the input to begin the count. And timer 2 is already counting, but the output's already triggered. So if I were to disable the machine, you'll see that the input timer has stopped, the output timer is counting, and the timer permanent, it just went along its merry way. I'll do it again, and you can see it just counts through the 30 seconds. So as long as LinuxCNC is loaded, the timer permanent will just count through to its set time, where the others kind of work in a wacky fashion depending on the current machine state. And you see that. So I'm going to reload LinuxCNC just to eliminate any of those temporary HAL commands that I was using. And I just want to do a quick couple of real-world scenarios for you before we move on. If I do a new to clear all data, go to my HAL configuration, I'll modify, I'll create my output, create an input, timer in the middle. I'll make it a permanent with a base or with a preset of 10 and a base of seconds, so 10 seconds. Hit apply, hit OK. Now let's pretend that this is a push button for our lube pump. Do set P, classicladder.0.in-10, set it true, set it false, so we pretend that we pressed the button, we release the button, the machine will now turn on the output that enables a relay to trigger the lube pump to run for 10 seconds. We're not running a production machine, so pressing the button every once in a while is fine for us, let's just say. But then there's times where this is a little too simplistic and you want a little bit more automatic operation rather than manual intervention. So in that scenario, we can make another line, another timer. We'll make them cycle for 10 seconds. We'll make them both on timers. Here we'll have an output. We'll call that B10. Up here we'll make a brake coil, call that B10. Down here we'll have a make coil, and we'll call that Q10. So now if we watch our little timer example here, the output stays off for 10 seconds. It's now on. The lube pump is running. Down at the bottom, it's counting for 10 seconds. And once that's done, it triggers the internal relay to make, which will then break this one and set this to true, and then this will just cycle around and around and around until you turn off your machine. So let's say we want to get a little bit more fancy schmancy with that, and we want to only make it so that the lube pump runs after the machine is in a happy ready state. So we can go in to modify, and we can just create another coil with an input value of, well, we're still using I10, so we'll say I10. And we'll tie that input 10 to net machine-on to classicladder.0.in-10, and we'll use halui.machine.is-on. So now that the machine is on, the lube pump will wait 10 seconds. It'll turn on for 10 seconds. And it'll just cycle over and over and over. So there's a couple ways you can make these cyclical timers. This is just one example of it. So I'll save that for just in case. So now I want to get into counters. And counters are different from timers because timers have a set value for when they will either count up or count down. A counter will take in user input and store that inside of a little memory section to help tell when an output should be triggered based on the amount of input that has been put into the counter, essentially. If I go to my modify here and I create a circuit with a counter, now a counter has a lot of different user input and it has 3 different output settings. So the inputs are R for reset, P for preset, U for up, and D for down. So let's think of a case where we're running a certain number of parts and we want some type of user input, say a button, to count up every time we make a part. But then if we make a mistake on a part, or if it's out of spec, we can take away that value or take away that one part from our total count. So, thinking of it that way, I go back into my editor. I'll create a couple of inputs. And I'll say that this one is I12. This one is I11. And this guy here is I10. If we click on our counter, the counter only has 2 values. The counter number, which is in this case C0, and then the preset value, which is the max number of count that we want to apply to this counter. The 3 values that tie to outputs are an overrun, an underrun, and a preset count value. So we'll use Q10 for our happy output. We'll use Q11 and Q12 for our not so happy output. So right now we have no values going anywhere. We have inputs, we have outputs. If I go to my HAL command and I say set p classic ladder dot 0 dot in dash 10 is true, all that does is resets the counter to 0. If I say classic ladder in dash 11 is true, it pulses a count. If I say true again, or in this case I'll just use 1, counts up, counts up, counts up. If I wanted to override my current number here, I would have to tie a value to this preset here. To do that, I would use one of the floating inputs or S32 inputs that are available to me in LinuxCNC and Classic Ladder. If I didn't want to do that, I would just use the up count and the down count. So we'll stick with this example for right now, and I'll say, okay, well, set p classic ladder dot 0 dot in dash 11. We'll just keep truing that up. So now once we hit the 10, we'll see that the output now gets triggered, regardless of what I have here for my up or down buttons. The output's triggered, and the event is now happening. The event could be a relay that ties to a flashing light, and now the light is flashing to say that the count has been met, or it could be an alarm that goes off or something like that. During my production, I noticed that there's a part that is bad, so I could use a down count, or say 2 parts, and now we're back to 8 instead of the 10, using input 12 to count down instead of up. Now, as far as the up and down count goes, you'll notice a little little something something when I get down to a 0 count. If I do one more of a 0 count and I go to 9999, this output E is going to trigger because the counter has been underrun by the user interface. So what you can have is you can have it, if you press the down button too many times, you can have it trigger an alarm that says you hit the down button too many times. Or you could just write in logic to where it won't ever do that. But you have a couple of underflow and overflow settings. So if you look at the LinuxCNC help, an underflow is where an output will be true when the count rolls from 0 to 9999. And you have an overflow, which will be true when the count rolls from 9999 to 0. So if you're counting over 10,000 pieces, you could actually tie your overflow and underflows to different outputs that will trigger events in ladder to either reset the count or store the count in a different area, or there's a bunch of different things that you can do. Which leads me into a segue of using variables. Now this p value here I can use with floating point or S32 input value to write the preset value within my counter. To do that, it's not as easy as just defining a bit here or an input here. We have to define a floating input. So that lets us touch base on a couple of the other bits or pins that Classic Ladder affords us. We have float in, we have float out, we have S32 in and S32 out. So a floating input is a decimal value, an S32 input is an integer value, and floating value allows you to have decimal place, 1.111 whatever, and S32 is an integer value, which is only whole numbers, 0, 1, 2, 3, etc., etc. So what I could do in this case here, because I can't just do IF1, you wonder what that means. IF1 is a floating input. So to get to there, I go to the VARs menu and I go to my watch window. You can't see floats or S32s through the bit management, so you have to do it through the watch window. So here I'll do IF0 and I'll use a float value. It changes the memory switch to floating pin. Here it shows me a decimal, and then here it shows me the current value. And if I want to use an S32 input, I would use IW0. So here we have floating pin, S32 in pin. I can use decimal, hex, or binary values to view the inputs coming into both. With this watch window active, I can then do set P classic ladder dot 0 dot float. Let's just double check. Float in dash 00, and we'll just say 32, and we'll see that the value coming into Classic Ladder is 32. We can do 32.1. It'll float in decimal values, but it will not display them here. Same thing with the S32 pin. So set P classic ladder dot 0 dot S32. See what that's called. In dash 00 35. And we'll see that it floats in a whole number value of 35. In order to make our preset value become active and use these float or S32 pin values, what we have to do is we have to do a little bit of variable work. So now, as far as the preset values go, it's not just it's not as easy as put value to the preset pin. To show you that, I'll use I14, and I'll say set P classic ladder dot 0 dot in dash 14 is 1. all that's doing is overriding the counter and triggering the output. So you can use this to bypass the preset value and just trigger the output for whatever reason you would want to do that. The way to get around and set values from LinuxCNC to the counter would be to, well, first we'll delete this because we don't need it. Down at the bottom, I'll put in an input, and again we'll use input 14. But what we're going to do is we're going to use a variable assignment. And the variable assignment is going to say counter 0 dot p equals %sign if 0. And we'll get into variable assignments and expressions in another video, but I just want to show you before I enable this, if I hit OK, I currently have a preset value of 10. I've got this input that's taking in a float value. It's going to assign it to counter 0 preset value. Looking at our float value is 32. Our preset value is 10. If I enable that input, and click on the counter again, you'll see that the preset value changes to 32. So now the plot thickens because we can take in float values from somewhere or S32 values from somewhere and apply them to counters via input assignments, or output assignments if you want to get technical. Taking in input and outputting an assignment. So to show you that a little bit more in depth, I'm going to go to my machine sim that I have set up with the Glade parts counter that I've created. You'll notice, if you've been following my videos, you'll notice that the parts counter is slowly evolving a little bit. It's getting a little bit more bling to the bottom of it. So I'll home this out real quick. Now if we look at this parts counter example, you'll notice that I just have a reset pin, a count up pin, a couple of outputs that trigger after the count has been reached, and then underneath that I've got a series of assignments. So the input to assignment is set to the count set button in my Glade panel. Input 1 is set for count up. It's also overridden by this I3, which is the override button. So I'm using this panel to speak interactively to this counter to tell it that I want a count of 40 pieces, hit count set, click on the counter, and we see the preset value is 40. If I go to this box here and I want to say, okay, I've already got 10 pieces in my inventory, count override, it sets the current counter to 10. This variable assignment here is all I needed to trigger the reset to set the counter back to 0 here, and also reset the counter here in my panel. So if I hit count reset, it now sets my part counter back to 0. So these variable assignments will become very useful once you get the hang of using them. But you can see that as far as a counter is concerned, it's pretty simple. Use the reset button to reset the counter to 0, and use the up pin tied to an input to count up. After it's reached a count, send an output, and that's it. The counting I actually have tied to this input here via custom user M code, which is doing nothing more than taking a ladder input assignment, classicladder.0.in-01, toggling it on and off, and using that as the pulse for counting up. So if I go to MDI, trigger M189, which is my M code for part count, you'll see that the count increases. And every time I do it, the count will increase more and more. If I change my maximum set count to 5, and I override my count to 4, if I trigger that M189 again, it triggers these two outputs. And these outputs are for program stop, which will actually trigger the auto program stop, which is this button here, and it will trigger this little LED to turn on to tell me that the count has been finished. So as you can see, we're setting the foundation for building blocks that will lead us to more and more advancements in LinuxCNC, more enhanced usability in Classic Ladder with LinuxCNC, and for more and more larger scale projects. So stay tuned for some more tutorials. Thank you for watching this one, and please like and subscribe, and hope to see you soon.